Hello, everyone. Thank you for coming to this talk. I'll be talking about efficient distributed orthonormal optimizers for large-scale training. My name is Kwangjun, and I'm with AI Frontiers. So what is this talk about? Motivated by the current situation where a lot of compute is going into training AI models, we would like to make the training more efficient. And to tackle this question, there could be many different approaches, like coming up with better AI model design, architecture, or coming up with better data, and so on. But today we're going to discuss training itself more directly. So let's review how AI models are trained in 3 steps. So you have data and model setup and training code base. Then data goes into forward pass and give you the loss. And the loss after backward pass give you these vectors and matrices called gradients. And then gradients go into the optimization algorithm, like Adam. And then, and this gives you weight update. And then it repeats and so on. And today we're going to focus on this optimizer part of training specifically, because it's giving you the weight update to get the optimal parameter configuration. So in particular, today we're going to talk about a new family of optimizers and their implementations. So we're going to first introduce this new family of optimizers called orthonormal optimizers, and then how they're implemented for large-scale distributed training. And then we'll discuss strategies to further improve its scalability, and then how you can integrate this into your code base. So during the talk, if you have any questions, please feel free to ask. A lot of the things that we will discuss in this talk, you can find some of the implementations in our code base, Beyond code base. And I'll point you to other relevant references throughout this talk. All right, so let's start with the introduction part. So what is the orthonormal optimizers? This part will be slightly theoretical because I want to show you what theoretical principle this optimizer is built upon. Mostly based on this excellent blog post by the inventors of Miwan. So in AI model training, the current de facto standard is hands down AdamW. And you can show the popularity of this algorithm based on the number of citations the paper received over the last 10 years. It also got the Test of Time award from iClear last year. So given that it's so dominant in AI model training, the question here is, can we actually do better than AdamW? So let's look at what Adam does. At a high level, AdamW algorithm computes the weight update based on the gradients element-wise. So it's element-wise operations, which makes it very efficient for distributed training. But it also means that the algorithm is treating each parameter scalar independently, as if they're independent scalar. However, most parameters in the modern neural network architecture are not independent scalars. They're, in particular, matrices that transforms input vector into output vector. So here's a nice diagram from Jeremy Bernstein. So input activation comes in, and then hits the matrix parameter, and then output y comes out. So the question is, with this structure in mind, since a lot of the parameters in the neural network are not independent scalar, can we design better optimizers for them? So in fact, this question has been explored several times in the literature, and there are by now several matrix optimizers. But today we're going to focus on orthonormal optimizers, or widely known as mu1. So why? First, I like this approach of orthonormal optimizers because it's based on a very simple theoretical principle, and it has shown very strong empirical benefits. And I'm going to show you what I mean by this in the next couple of slides. So before that, let me show you what mu1 update rule looks like. So given a parameter W, matrix parameter W, it gets updated with this learning rate eta, with this scaling factor, which is determined by the input-output vector dimensions, times the most important part, orthonormalize G, where G is the gradient matrix. And the orthonormalize operation is defined as follows, where for matrix G, which has singular value decomposition, use sigma V transpose. Orthonormalize G is skipping this sigma, the magnitude of singular values, and only taking the UV transpose. So in particular, this output orthonormalize is an orthonormal matrix. So why are we doing this bizarre update rule? So here I'm providing some theoretical motivation behind this. So recall that we have this diagram of input activation transformed into output activation by this matrix parameter. So the principle that we designed this orthonormal update based on is controlled growth of activation during each training step. So consider this weight update where weight W gets updated by the delta W to get a new set of weights. And ask this question of how this weight update affects the output, change in the output, delta Y, right? In particular, we want to understand this question, scale invariantly. So we're going to consider root mean square norm, which is just nothing but the L2 norm divided by the square root of dimension. So it's a dimension independent quantity. And we want to see how this quantity evolves after update delta W. With simple math, I'm going to skip the derivation here for simplicity. You can show that the change in RMS of this delta Y output is bounded by the scaling factor, square root of fan in over fan out times the spectral norm of this weight update. So what this inequality is showing you is that as long as you keep the spectral norm of the weight update bounded by this quantity, it guarantees you that in worst case, delta Y is RMS norm is bounded by some desired target eta. Okay? So given this, now the question is, let's try to maximize the alignment between this update delta W with the gradient, because that's the where the descent of the training loss happens, subject to this new spectral norm constraint. And after doing some algebra, you can see that the maximizing solution is the mu1 update I showed you earlier, where you orthonormalize G to maximize the alignment, yet you can achieve the spectral norm constraint. So the derivation is pretty simple based on the this simple theoretical principle. Here you might ask, so how are you doing this orthonormalize operation? It turns out can be efficiently computed through Newton-Schultz iteration. And it consists of nothing but matrix multiplications and additions. So it's very fast on GPUs. So it's basically repeating this matrix polynomial iteration. And you can efficiently implement this on GPUs. So how do you choose these coefficients for the polynomials? The original inventor of mu1 somewhat manually chose this coefficient to achieve this goal of orthonormalization. And I would like to introduce to you another recent work from last year that came up with a more systematic approach to came up with coefficients ABC called the polar express. So those who are interested, please check this paper out. Okay, so far I talked to you about the very simple theoretical principle that you can use to derive this new set of update rule for matrix parameters called the orthonormal update. And now you might ask, okay, so it has a clean theoretical principle, so what does this really buy us? Turns out it's very strong empirically, and let me show you some of the evidence from the literature. So first benefit is more motivated by this theoretical principle of controlled activation. And if you think about it, across different scale you're training the models at, if you can guarantee that the activation scale is controlled, it can successfully train. So with this principle in mind, actually it turns out this orthonormal update rule with the right scaling gives you direct transfer across scale. So what I'm showing you is the training loss against the learning rate, and different color of the curves corresponds to different size of the model. And the plot this one is highlighting is that across different scale, the optimal learning rate lines up for dualization in this plot. But dualization is nothing but the orthonormal optimizer. And you can see that the alignment is very much cleaner with the orthonormal updates than like traditional standard parameterization of Adam, for example. And for language modeling experiment, there's this very nice paper from last year ICML called Cyan, where the authors show that this orthonormal update mu1 with some slight modification can give you very nice alignment. This plot is the similar spirit as the one above, where across different scale, you're just sweeping across learning rate and see which one gives you the optimal. And you see that the alignment is very clear with this recipe. So in general, orthonormal updates or optimizer gives you clean hyperparameter transfer. That's more benefit coming out of the theoretical principle. But another benefit that's somewhat surprising, because it's not really part of the theoretical motivation, is that the fact that the optimizer is gives you very fast training, faster training than AdamW. So here I'm showing the result from Moonshot AI, which demonstrated the twice flops efficiency compared to AdamW for training this total 16 billion model, MOE model. So in general, in the community, you can see this from Nano GPT speed run and so on. This mu1 or orthonormal optimizers gives you really faster training than Adam when used properly. Next thing is perhaps like has more practical values here for large scale training is the fact that these orthonormal optimizers are very friendly with larger batch. So for this, Essential AI conducted a very nice study on this, where they have the result showing this trade-off between the number of GPUs versus the total training time. So in ideal world, if you're willing to spend twice more compute, the total training time should be, so I mean, if you're willing to train on twice more GPUs, in ideal case, we should get like half total training time. But in reality, with, for example, AdamW, it has the critical batch size, beyond which it only gives you plateau gains. And so the ideal trade-off you want to follow is this 1/x trend. And you can see that mu1 traces better trade-off than AdamW on this front, showing that it's much more suitable for larger scale parallelized training. Last thing is the perhaps also coming from the theoretical principle, because we're controlling the activation at each training step, it gives you more stable training. For some evidence is the Moonshot AI training the Kimi-K2 model. They observed that for this really large scale mu1 or the variant of mu1 orthonormal update, they developed mu1 clip, gives you very stable training dynamics, which is quite remarkable for this large scale training runs. Okay, so these are the benefits. So we're going to talk more about this orthonormal optimizers and how they're implemented for such large scales. But before that, I'd like to go over some of the recent highlights in algorithmic improvements. So let's revisit the mu1 update rule. For matrix parameter W, we have this orthonormalized update. So before I said it's orthonormalized G, but actually in practice you use M instead of G, momentum, where it's basically weighted average of gradient across time, and just to improve stability. And it's a standard trick in training AI models. So another way of looking at this, for those who are familiar with optimizers, it's basically you're orthonormalizing known existing optimizer called SGD momentum. So upon seeing this, the natural question you can have is, what if we orthonormalize more advanced update rule, right? Such as Adam, because like Adam is known to be better than SGD momentum. So that's precisely the approach taken by some of the colleagues from Microsoft with collaboration with Georgia Tech called NorMu1. So I'm gonna quickly talk about what they did. So they consider basically orthonormalized of Adam-like update. Let me show you some details around this. So they consider row-wise Adam update, also known as Adam mini update. So you have this momentum aggregation, but for second moment estimation, you actually take the average across the column so that you have this row vector size second momentum, and you divide with this square root of V to come up with this Adam mini-like update. And what they did is basically orthonormalize this advanced update rule than SGD momentum to come up with their optimizer. In fact, if you go through their paper, they noticed that if you swap the order of orthonormalize and Adam, so for the interest of time, I'm not going to go into the details of this. So swapping the order is a little bit more helpful. So that's their final design of the algorithm. But roughly, the main idea is to orthonormalize more advanced update rule. Okay, so this is a bit technical for those who are not familiar with Adam, but you can just think of it as, okay, you have this mu1, which is orthonormalizing HDD momentum, but you can actually get more gains by swapping out HDD momentum with more advanced update rule like Adam. But I guess for those who are not familiar with Adam and so on, you can regard this as some advancement in the update rule, algorithmic improvements. And concretely, this new algorithm set the new world record in GPT speed running, so showing the validity of this idea. And we actually have implementation of this algorithm in our Dion code base, so you can also try it out with larger scale run with FSDP. Another algorithmic improvements that I want to touch upon before I move on to the implementation details. So to motivate the orthonormal update rule came out of the principle of this controlling spectral norm of delta W, weight update. The next simple question is, what if you also want to control weight, the spectral norm of weight themselves? This idea was explored in Microsoft Research Asia and other their collaborators called Control LLM Training on Spectrosphere. So they basically add on top of this mu1 orthonormal updates, which is controlling the spectral norm of the delta W. They also add spectral norm constraint of the weight themselves, and they have some numerical procedure to solve that. And they observed quite striking results in their paper. For more results, check out their paper. And what I'm showing you here is the activation dynamics across training. On the left-hand side, we're showing the activation maximum outlier. And on the right-hand side, we're showing the RMS, root mean square. And you see that compared to AdamW mu1 baseline, the spectrosphere, which is explicitly controlling the spectral norm of each update, each weight as well, is giving you very stable dynamics, which could be potentially very helpful for very large-scale run or even for low-precision training. Okay, so this is pretty much the like the introduction of orthonormal update rule that I want to talk about for now. And let me move on to the implementation side of distributed training. If there's any quick question, I would love to answer. Otherwise, I'll move on to the second part. Okay, I'll just keep going for now. So implementations for distributed training. This part, I'll largely based on this excellent blog post from Essential AI. So to set the stage for the discussion, how are the large models trained on GPU clusters? The goal here, roughly, or precisely actually, is a strong scaling where you want to increase your throughput of the entire training proportional to the number of devices you put in, right? Intuitively, if you put more GPUs into training, you want to get out more from the training, right? So the question, very important question here is that given the model size and the number of devices, can we achieve this strong scaling? And it turns out it's not a trivial question, requires a lot of careful thinking and careful orchestration of various competing goals, such as memory usage, compute efficiency, and communication overhead. So to attack this challenge, there have been proposed many parallelism strategies, such as data parallelism, model parallelism, and parallelism that sits in between called 0, 1, 2, 3 technology strategy, as well as fully sharded data parallel. Okay, so given all this, as an optimizer designer, you should really think about whether your new optimizer is distributed training friendly. Because given your infrastructure of your training run, the combination of this parallelism strategy that I mentioned in the previous slide is determined to maximize the forward backward part of your training efficiency. So roughly, given your infrastructure, the parallelism strategy is fixed. So as an optimizer designer, your role is to make your optimizer compatible with all these parallelism strategies. This is some illustration from this Hugging Face showing the, based on infrastructure, there's roughly optimal strategy you can take. So for the remainder of the talk, because with this orthonormal matrix optimizer, it's tricky to do this matrix operation when things are sharded. So we're going to focus on how to implement this orthonormal optimizers when these matrices are sharded across different GPUs. Okay, so the quick question is, how can we orthonormalize a given matrix in the distributed fashion when things are sharded? So we're going to discuss this based on toy version of this Newton-Schultz iteration I talked about. For now, we're just going to goal is to compute the fifth power of matrix G. So this is like the toy version of Newton-Schultz implementation looks like. So when things are sharded, just to motivate, if you don't do the distribution carefully, you can actually burn significant amount of flops with this computation, which makes this approach infeasible at really large scale. So you really have to think about how to distribute this computation more carefully. So the question here concretely is how to evenly distribute the Newton-Schultz computation when the gradient matrix is sharded across X devices, say. So say if the gradient matrix has shape m comma n, and let's say each shard has a shape m divided x comma n. So I'll discuss how to achieve this based on various strategies. So two simple approaches you can think of here is that since the gradient matrix shard is sharded, what if you just all gather up front and then launch this for loop iteration? It'll be like this. So starting from the small g, you all gather to get g, and then launch this Newton-Schultz iteration. It's simple, but the downside here is that there's too much replicated computation because, again, the same matrix is sharded into various devices. So if you all gather them and replicate this computation, that's too much replication. For example, for Llama 3, 405 billion scale, there's like roughly 1,000-way sharding. So you're replicating computation over this 1,000 dimension, which is too much. Okay, so then what if we just stick to the sharded matrix multiplication? Like naive approach here would look like every time you need the full matrix for proceeding with the Newton-Schultz, you just do the all gather, right? Well, I mean, this way, all the computation is evenly sharded. But the problem is it requires a lot of all gather, which can also come at non-negligible or significant amount of overhead. So in other words, it's too much communication. So then what would be like the alternative that you can take to strike the balance here? It's Essential AI's all-to-all approach, where so you can actually use all-to-all communication collective to evenly shard this muon computation is the key idea. So we say that each shard has the shape m over x comma n. And what you can do is we batch x such identical shapes to come up with this batched version, x comma m over x comma n. And then use all-to-all collectives to efficiently reshard across batch dimension and gather them back together. So here is the illustration. So on the left-hand side, you have shards saved across this number of devices. And then you can all-to-all gather to have fully reconstructed local matrices in each device. And you can come back with the all-to-all scatter. So mathematically, or with the equation, you can basically go from G all batched, so batched shards with the all-to-all to G, capital G local, where it's now sharded across the batch dimension. So then now you have the full matrix locally, then you can do the matrix computation. And what makes the all-to-all approach quite nice is that all-to-all communication collective is quite efficient in modern GPU clusters, specifically on ring networks. It's about 4 times faster than altogether. And that's perhaps the reason why it's used extensively in the expert parallelism for MOA models. So this altogether gives you all-to-all mu1 approach where you start from the batched shards, lowercase g all, and use the all-to-all to reconstruct full matrix locally, capital G local, and then you can run the neural networks as if you had the full matrix on each device. And this is taking care of different matrices across device, so computation is evenly sharded across all-to-all ranks. And then you can do all-to-all again to get the batch shards again to get ready for the next 4 backward passes. So in other words, 2 all-to-all communication collectives will evenly shard mu1 computation across that dimension. And will let us scale mu1 even to larger training runs. The implementation of this all-to-all mu1, you can find it in Dion codebase, and I'll talk about this a little bit more later. Okay, so this is the basically how you can scale things up. This like matrix computation across like this distributed training strategies. Now let me discuss some further improvements that's been done in the literature. One nice work from this motive technologies, they demonstrate that you can actually optimize scheduling for this all-to-all communication to maximize the throughput. So the above will be naive version of all-to-all mu1, where you do all-to-all gather and then launch the Newton-Schultz computation, and then the all-to-all scatter after that. But then obvious thing to do, which we did in our Dion codebase too, is like communication computation overlap. You can add that to have the more efficiency. What motive technology did is a more fine-grained scheduling of this, where they do this chunk-wise overlap between computation and communication to maximize the network bandwidth. And then also they consider this a balancing workload based on the parameter shape, so that there's no imbalanced distribution of work to also maximize the overall throughput. So for those who are interested, check out the paper, and I'll also share some references later on. Okay, so lastly is about the approaches for 0-1. 0-1 strategy would actually have sharding for the momentum, so like the optimizer states. And this is worth discussing at this current time, because modern large-scale training runs extensively uses this pipeline parallelism and expert parallelism, which prefers 0-1 strategy over fully sharded data parallel. The point here is that under 0-1 sharding, distributing mu1 computation becomes a bit easier because you can technically have different sharding for your optimizer states than your parameter and gradients. Actually, in 0-1, parameters and gradients are not sharded, so you have a lot more freedom for choosing the sharding for the optimizer states. So in particular, if you opt for this flattened buffer sharding, only boundary pieces get affected by shard. So you only have to locally gather them to have the full matrix locally. And this is precisely the strategy taken by Moonshot AI to train this Kimi-K2 model. But unfortunately, the modern newer releases of the training frameworks, these large-scale training frameworks, don't support this flattened buffer sharding anymore. So we have to come up with different strategies. Although, except that in Megatron LM, they're looking at some new way to do 0-1 sharding, where they align the 0-1 sharding with the parameter boundaries such that we don't need this small localized gathers that the Kimi team did. And also they consider some load balancing. So the gist of what I'm trying to say is that for 0-1 sharding, there's some freedom of choices you can do to make the things more efficient. And that's indeed what Kimi-K2 was doing. And there are active ongoing research and development around this. So stay tuned to this. All right, so that's about it for how this orthonormal update optimizers is implemented across this distributed training. And I'll talk about strategies to further improve its scalability based on this Dion approach. So we have discussed like various strategy, and sometimes this all-to-all mu1 and stuff will make things feasible at certain scale, but if you scale up even more, then it could be a bottleneck and so on. So the scalability of this mu1 and orthonormal updates are actually really tricky. And the main reason is because AdamW is element-wise operation, so there's no bottleneck at all across scale. On the other hand, Newton-Schultz itself is a super linear operation, which becomes heavier and heavier across scale. And also, I discussed all this communication overheads for distributed training. So inherently, there's some contention, conflict with this orthonormal updates ideas with this distributed training and larger training runs. Okay, so can we actually have some approach that can future-proof all this scalability concern? So in the Essential AI's research blog at the end, they said all this strategy, all-to-all mu1, make things manageable at some moderate scale. But in the end, really, like we need to be able to shrink the matrix size that goes into this Newton-Schultz subroutine, in order to further scale up this idea. So that's precisely like where our work, Dion, and actually Dion 2, the newer version, lies in. It's a very simple approach to shrink the matrix size in this mu1 routine. So roughly Dion 2 has a scalability knob that's called alpha that sits in between 0 and 1, which governs the fraction that you orthonormalize. So if alpha is chosen to be 1, that's basically mu1 because you're orthonormalizing the entire 1.0 fraction. While if you decrease the alpha and it's strictly less than 1, you're only orthonormalizing a fraction of matrices. So here's the result preview of Dion 2. So on the left-hand side, I'm showing you the optimizer step micro benchmark. So I'm showing you comparison between mu1 and then 0.5 Dion 2 alpha is chosen to be 0.5, and alpha is chosen to be 0.25. And you see that there's computation saving because we're only orthonormalizing fraction of it. And on the right-hand side, I'm showing you the quality of this update comparison by showing you the training run validation loss across steps. And you see that even when you're orthonormalizing a fraction of it, it's still very competitive with the original mu1. So how's Dion2 designed? It's actually very simple, and that's a remarkable property of it. So basically, given the matrix, you only select alpha fraction of the rows based on the row norms, which is very easy to compute. And then select this submatrix and only orthonormalize this submatrix. And then using this submatrix to update the parameter. So it's a sparse update. And the important part is that this error feedback mechanism, the fourth step, where we only decay the selected rows in the momentum. And this is enabling us to choose diverse neurons and update them across different training steps. So Dion2 builds on Dion, our previous algorithm, and also this other algorithm called Trion. And they both orthonormalize this low-rank approximation of this momentum matrix. And we simplifies both of them by using this fractional orthonormalization approach. So let me quickly show you some experiments with Dion2. So what I'm showing you is for, first of all, 300 million model, showing you this training runs and compare it with mu1 across various alpha fraction Dion2. And you see this like trend where as you decrease the fraction, Dion2 becomes weaker and weaker. But then the important question is what's the trade-off compared when you're decreasing the alpha, how much update quality you're sacrificing? And it's actually very competitive. For example, if you compare with Dion, it's actually achieving better trade-off here, where across different fractions, it's actually beating Dion. So it looks like it's a better approach. And we have some experimental results for larger model, like 1B model. And you see that the larger model, it can actually it seems to tolerate smaller fraction alpha, because for this 1B model training run, 0.5 and 0.25 only came with very minimal sacrifice in the update quality. And let me show you some of the experiments that we did when we were incorporating Bion and Dion to Phi model series within Microsoft. So for 7B model, this is some preliminary experiments we did. Compared to the Adam, which is in green, and Bu1, which is in black, Dion was doing very competitive performance. Seems like it's the approach is valid across different scales. Okay, so I discussed this Dion2, which is the approach to make the orthonormal optimizers more scalable at various scale and make this idea future-proof. So I would like to wrap up this presentation by talking about how to integrate these optimizers to your code base. For the interest of time, I won't be able to going through the code examples and whatnot, but I'll keep it at a high level and pinpoint important points that you should keep in mind when you're incorporating this to your existing training code bases. So my general suggestion is to start from existing implementations, because around the excitement of this optimizer, there have been lots of open source implementation of this. So to name a few, both Torch and Keras training frameworks have their own Bion implementations. And for distributed training, the 0.1 implementation, and also the one that's ongoing progress can be found in Megatron LM. And for FSDP implementation, all 12 mu1 specifically, which is as we discussed, efficient. You can look at the Dion code base, which is based on PyTorch detensor-based parallelism. And motive technologies, the more further optimized strategy, can be also found in their Hugging Face open source the codes. So you could look at them and see which one suits your training code base and try to incorporate. And then let me talk through some of the important details while you're incorporating these optimizers. The most important thing is that probably it wasn't highlighted in the earlier part of this talk is that we're actually using two optimizers. Just because we are using Dion2 or mu1, et cetera, we're not using entirely on this because the modern AI models both have matrix parameters and scalar parameters. So for matrix parameters, you're using mu1 or Dion2 or like other orthonormal optimizers, while we should use other scalar optimizers like AdamW for remaining scalar parameters. So because of this hybrid approach, there are two important details here. You have to be very careful about parameter grouping, namely, so which parameter group you use mu1 or Dion2, and which parameter group are you using AdamW. And also because you're using two different optimizers, you have to choose the scale up the learning rate carefully to make them compatible. So I'm gonna briefly talk about how you can achieve these two goals of parameter grouping and then learning rate scaling based on mu1, and Dion2 works out of the box with the same setting as mu1. So for parameter grouping, like I said, mu1 handles matrix parameters. But then the important thing is like not all matrix parameters, which makes things a bit tricky when you're integrating. So you have to pay attention to this. Is actually hidden linear layers with dense inputs and outputs. That being said, it's not suitable for embedding layers or final classification layers or LM heads, because for them, either input or output are meant to be sparse. So it doesn't qualify for the mu1. So for them, you have to use AdamW, for example. And the practical rule of thumb when you're integrating this new optimizer to your code base, I mean, I cannot speak for all the different components people are using for neural network. So when in doubt, start using AdamW as you were just training before. And then you can be more careful about whether you can use mu1 on this one. So you start with the AdamW first, and later, if you really want to get things right, you can carefully think about each parameter roles based on the principle I was talking about. So what is the input vector for this parameter unit, and what is the output vector? So based on that, you will get some clarity on how you should integrate mu1 or other orthonormal optimizers to your architecture. For example, a good exercise here is that based on this principle, how you can do this like 3D, 4D convolutional filters in the convolutional neural networks. Last thing that I want to emphasize for the integration is the learning rate scaling part. Because we're using two different optimizers, having the learning rate compatible between the two is quite important. So there are actually various versions of mu1, and I'm not going to go into the details of them, but just to point which one to look at for your integration. So if you're integrating mu1 for the first time in your code base, I recommend starting with the Moonlight, which is basically Moonshot AI, who trained the Kimi-K2. They have their own scaling, which is to match mu1's RMS with the AdamW. So you're just, the great thing about this scaling is that you can just keep the same base learning rate as if you're using AdamW. So makes the integration pretty simple. And then if this integration with this moonlight scaling or moonshot scaling works stably, then I recommend gradually switching over to mu-p scaling, because it will give you this LR transfer property that I was talking about earlier in the earlier part of this presentation. But it will require some work. So for that, I'll refer you to like all these references that I talked about to get the right idea for how to get the mu-p scaling correctly. Yeah, and another thing is with mu-p, you cannot just directly use the AdamW training configuration you've been using for mu1, and you have to freshly tune the correct hyperparameter. Okay, so these are the practical guidelines I want to highlight in your integration. So I'd like to wrap up with some summary. So I talked about the theoretical principle of how orthonormal optimizers are designed and the practical benefits of them, and then talked about how these guys, because they're different than AdamW, element-wise operation, how are they implemented for distributed training setting, and then discuss strategies to further improve its scalability, where I talked about our approach called D-on-2. And then I discussed the guidelines for incorporating these new optimizers to your code base. Yeah, so this is all I have for today. And yeah, thank you for your attention.
You're getting some applause online also.
Thank you. Go ahead, please.
Thank you very much for a great talk. I just had a question. Can you explain again why using these orthonormal optimizers on, let's say, the embedding layer is not appropriate?
Yeah, so it's like, because if I give you a more precise answer, when we're driving this orthonormal optimizers, we're using this RMS norm to measure the progress. But RMS norm is not really a good metric for measuring the progress for sparse vectors. So that said, you should use this orthonormal updates for dense input to dense output type of matrix parameter. But for embedding, for example, think about it, embedding, you have one up vector goes in and get the this embedding, vector embedding. So it's really like sparse input comes in and the dense output comes out. So it doesn't qualify for this theoretical principle. So hence you cannot use mu1. And what's a nice thing about this theoretical principle is that you actually start using mu1 as if it was a dense to dense vector transformer. It will like not give you this strong empirical benefits you observe with mu1. So it's like very consistent with theory. But yeah, just to keep it short, it's not this dense to dense transforming matrix parameter. Does that make sense?
It does. Thank you very much.
No problem. Is there other question in the audience?
Hi, I have a question.
Yeah, sure.
Do you know what, this is probably more speculation than like hard evidence, but do you know like what the biggest, best, etc. model that's been trained with these like orthonormalized approaches are? like a DeepSeek, a Qwen, GPT. Like probably GPT we don't, but like yeah, do you have a sense of like how well validated these ideas are at like the kind of more
Yeah,
cutting edge, I guess?
John answering the question, Kimi-K2, which I discussed like when I was talking about this 0-1
Okay.
strategy. It's a total 1 trillion parameter. And I think, yeah, it's the biggest scale it's trained on. And to answer your question about like the importance of this, because it has a lot of this strong empirical benefits, I mean, obviously we cannot speak for like these labs which are not open sourcing or like letting people know about what their training looks like. But it seems like circumstantially a lot of frontier labs are seriously moving into this new optimizers. Does that answer your question?
Yep, thank you.
No problem. Is there any other question?
I don't see any hands up.
Yeah. Then yeah, thank you for attending and have a great day.